All right, in 12.2b, we're going to do one more type of transformation to achieve linearity. It's called the exponential model. So how do you linearize a relationship that follows exponential? Well, the exponential model looks like this. You're taking the logarithm of just the response variable, not the explanatory variable. So again, you can use the common logarithm at the base of 10 or the natural logarithm at the base of e. Either way, this is called the exponential model. So let's try an example here. The April 1st, 2011 edition of the Arizona Daily Star. The following data was presented about mandatory fees at the University of Arizona. Letting X represent Ford for 2004 to 2005, graph a scatter plot. Does this relationship look linear? So if I put this in my calculator and I graph a scatter plot, this is what it looks like. This looks like it's exponential, not linear, right? It's definitely curved. So then my question is, well, is it exponential or do I use power model? Which one do I use? Now, the good news is, really, it's just looking at final results of the residual plot to make that decision, but I'm going to show you how to do that. All right, in B, sketch a scatter plot of the natural log of fees versus the year. Calculate the equation of the least square regression line and sketch the residual plot. So, all that to say, what I'm putting my calculator here. List 1, I'm putting the year. List 2, I'm putting the fees. List 3, I'm taking the natural log of fees. And then when I do my regression line, since I'm doing the exponential model, I'm going to do X is my X list, leave that alone. The Y list is list 3. It's the natural log of my response variable. When I do all that, I then check my residual plot, or I'm sorry, not residual, my scatter plot. My scatter plot now looks a little bit straighter, and the equation that it gives me is this. Now the real question on is this the right fit is the residual plot. So when I look at my residual plot, this is what it looks like. There's really no pattern here, so that looks like it may be a good model. But we really don't know if it's the best one until we compare it to part C, the power model. Okay? Is it exponential better than power? We won't know until we look at the data. So to do power model, I'm going to go back to my calculator. In list 3, I did the natural log of list 2. Now in list 4, I'm going to do the natural log of my X variables. Then I'm going to recreate the regression line, but this time my X variable will be from list 4. My Y variable will still be list 3. So I've taken the logarithm of both variables. Now, my equation comes out looking like this when I've taken the log of both sides. The scatter plot looks like this. It's straighter for sure. And then my residual plot looks like this. So just kind of glance at this. The exponential scatter plot and the power scatter plot, they're about the same. They're both definitely straighter than the original scatter plot. Now, but the big difference shows up when you look at the residuals. The exponential model does not have a leftover pattern, while the power model does. So part D says, based on your answers to B and C, would an exponential model or a power model be more appropriate? So, like I said, the most important thing to look at is the residual plots of the different models. And you can see, like we just said, the power model has a leftover pattern, but the exponential does not. So, which model makes more sense, makes it more appropriate? The one with no leftover pattern. So I would say the exponential model is more appropriate because the residual plot for the exponential model has less of a leftover pattern than the residual plot for the power model. Also, the scatter plot of the natural log of fees versus the year, the exponential model, has a stronger linear form than the power model scatter plot. It's just slightly stronger. Part E says, use the model that we chose in Part D to predict the fees for the 2012-2013 school year. Do you expect this prediction to be too low, too high, or just about right? All right, so we're going to put in 12 for the year. Remember, we're using our exponential equation. We just took the logarithm of the response variable. So this is what it looks like. So I can put 12 in for the year. Now I'm going to calculate all this, and I get 6.988. Then, remember, the base of a natural log is e, so when I swirl it to get the fees out of the logarithm, I do e to the 6.998 power, and that gives me the fees. So that's 1,083.55. So if this is the fees that we're predicting for 2012, what does our residual plot tell us? Well, if you look at it, for 2012, it looks like it would be going up. We'd have a positive residual, which means that our prediction would be too low. So I would say the trend on the residual plot suggests that the residual for x equals 12 would be positive. This means that the predicted fee would actually be less than the actual fee.